Well, welcome to Stats 1. We're in lecture 4. We're counting raptors. We're using integers. So why are we looking at the binomial model from the previous lecture? Well, simple reason. We're going to use this and repurpose it. We're going to add something to it. We're going to add a single piece of data. So instead of 8 tosses of the globe and 4 successes, which were water, that shows here, we're going to use exactly the same structure and change change very little. What we're going to do is we're going to use the part 3. That's a really good thing to go through here. A plot like this, we're going to simply change a title or 2. Yeah, just 2 titles, and work this out. Now, suppose our data is no longer n and x. It's just x, and that is the number of workers that we might observe at this undisclosed site in what many of us affectionately call the forgotten borough, called the Bronx. Some people think that's Staten Island. They want that notoriety, and we're just going to repurpose this. Well, let's start with the repurposing this way. Instead of p, we're going to choose a lambda, which is an intensity. It is a rate. It is a number per time unit, in this case about an hour, as described in the lecture. A very small unit of that time was flagged as 1/3600th of an hour or a second. 60 minutes, 60 seconds, and that's where that number comes from. We're still going to use an 11-point grid with 10 intervals, and our lambda no longer goes from 0 to 1. It's going to go from, in this case, we're just going to pick something here, from 10 will be the max. And you can see everything changes. It's a mess now. a wonderful mess. So don't let this ever worry you. From 10, we're gonna work it up from 5. So we're gonna go from 5 to 10 intervals still. Number problems everywhere. And instead of the binomial, we're going to use the Poisson distribution. And this is all in the lecture, as well as in the reading, which is counting raptors. That was a different example. The more examples, the better, the easier it'll eventually be. Now, we don't need n anymore. N is nonsensical. Watch this thing just go nuts. All we need is x. Okay. And this is 0.0909% roughly. And we have a lambda that goes in steps of 0.5, half a lambda, half a person. Remember, we're talking about average rates here, so this is okay. And we're talking, in this particular case, about 7 people coming in. Okay, we observe 7 people. And we still have x. Okay, we still have x. And in this particular case, we're going to type out, here's the formula. If this will work. E to the minus lambda, lambda to the x over x factorial. And x factorial keeps coming in because of a recursive relationship about first one person shows up and then another one does or does not show up, and then yet another does or does not show up. And then you count the number of people in the end who do show up. And that's where that recursive factorials are basically recursions. And that's how they come about. So let's type this in, not using binomial at the moment. We'll use the let's see if I can expand this a little bit. There we go. Equal exp for that e base. Base e is 2.718, etc. Raised to the minus lambda. And here we're hypothesizing this. Now let's we might want to copy this over to other pieces of data. There we go. And thus we will hold that address as absolute. The address component is the E or the column times. And then we go back to the lambda. Again, holding the address constant with a $sign. So far, so good. We want to raise this to the x power. Well, there's the x power. Okay. And divide that by the order of operations worked here. One of the last things that is computed is something we're gonna raise e to the x and then take that amount as if it's in parentheses and divide it now by the factorial also of x. And let's see what I got here. Fact x, e to the x, and it must have been an extra. Okay, so that turns out to be and I have the red wheel going on here for some reason or other. And it doesn't like the rest of this, obviously. So let's just copy and paste this all the way down. What did I do? Control C and then shift down arrow to do this. And now Control V. You see everything squares up all of a sudden. This is repurposing a perfectly good model. That's all it's doing. We don't have to reinvent the wheel every time. I want to change this. I want to change this to lambda instead of p. Repurposing of models. We do it all the time. Expand this in case some other human being needs to see this. There we go. Now, what's interesting is that whatever was over here should work, but you see it doesn't because there are a couple of problems. Problem number one, the lambdas only go from 0 to 1 because this graph remembers how the axis was formatted from 0 to 1. And now we want to do it from, let's do it from 5 to 10. There we go. And we have a lovely quadratic function here. much like we discovered in lecture 1. You might want to go back and look at that. And here it's not how much water, it's how many workers. And we don't need, there we go. I'm just going to edit, again, repurposing. We need is X. Instead of P star, we get lambda, which is the top rated, most plausible. Okay. And we come up with hopefully not a surprising result. I hope it's not too surprising. The optimal and that's wrong. Okay, I'm going to fix that. It shouldn't be G6. One of the things didn't completely go over here. Just let me come up here. Okay, I want to use this. I have way too many spreadsheets open, and that's why we're getting the wheel here. And you might, in a case like this, want to get rid of those so that you can actually edit the work. So I've fixed that little problem there down here with the title of a data series instead of P of PR of D conditional on hypothesis. It's hypothesis conditional on data. Now that's correct. And again, what we see here, get rid of the format for the moment. What we see here is exactly as in lecture 1, a very simple, and I hope nobody is surprised that the average of 7 is 7. Okay, it should be okay, the average worker. Now, what happens, however, if we have an update to this? And let's update this model to something else. And we're going to take the result, which are these plausibilities of hypotheses, and we are now going to use these to help us inform us of what our prior experience is. So we're updating. Well, we have a prior experience, and this is our prior experience. That blue line to the right there is our new prior experience. So let's copy and paste over here in F7, but paste, and if you don't do this, this will not work. Paste values only. Okay. See, things changed even more. You're getting a little twist in here. You see the twist starting to occur. Okay. And our new one is a little bit different, but not much. Let's see how much difference there is. Okay, that's the old one. Here's the new one. We haven't updated it yet. All we've done is use a different prior. Yeah, see, it's beginning to squeeze in a little bit here. look at the squeeze play. Yeah, just a little bit. Okay, now that's 6 where that was 7 and so on. And you're going to see this begin to occur, and it will be a phenomenon that people began to notice. Back in the 1700s, they noticed this without this calculator with sprockets and gears. Okay. Now we're going to update this. Now we're going to keep all the rest of this machinery over here in I through J, as well as all the machinery over here in the realm. We're also going to keep our lambda from 5 through 10. And we're going to add another, observation, another day's worth. We have 7, and this could have been any other day, by the way, because everything is going to be commutative. We're going to have to do something over here, rather, instead of that product. We're going to put in a different thing. As a matter of fact, we'll leave that for the moment. All we need to do here is add another column. So we go to insert a column. Nothing changed, you see. Nothing changed at all. And suppose instead of 7, we get, we observe 9 new workers. Okay, so we can use this with X, because I already had defined X, but really what I want to do is use something different here. I'm going to use the Poisson. It'll give you the same results. And now the X is going to be a 9 in this particular case. And we're going to hold the row as an absolute address. We're going to assume mean, that's what they're talking about, a lambda. It is a mean. Let's make sure we put a $sign next to that. How we make a table is we hold one side of a binary relationship, the row as an address constant, and the other side of the binary relationship, the column, will be a constant. That's why we make a multiplication table. That's a binary relationship, A times B, A binary to relationship times, okay. Right. And we need to do one more thing here. We need to declare what kind of a distribution this is, and we're going to say this is a probability mass distribution. Okay, and it's a false. Okay, I'm not going to do any cumulative here. And we get 4 for that one. But over here, we have a further problem. We have 3 things happening. We have a prior at 753%. We have a piece of data coming in from a Poisson point of view, and all the mental machinery around that point of view, it's 10%. And now we have another piece of data, 9, from that point of view, it's 4%. Both one and the other and the other. Let's just use the product function for this and do that all the way across. And we get 8% there, and things are going to start changing. Actually, what I want to do is copy those all down. Now things begin to pinch in. Okay. And now we have a new plausibility curve. This is the blue curve right here. And I think we are now averaging 7.5, given these 2 pieces of data. And that's also given the prior experience. So what if we want to do this again? This time's a little bit easier. Just put your cursor here between the 7 and the 9, add a new column. Suppose we observed only 5 workers this time. And let's use this Poisson formula here. That's very close. That's a lot closer than 9, so the probability should be higher to that lambda. Okay. And notice that copies over nicely because we again fix the row, but we also fix the column, which is the column E, where all the lambdas are. And let's do this. Copy it down, and things change again. Now, what I didn't do that I should have done. Okay, let me go back and undo all of this. Okay, that's what we had originally. Is let me use the experience of adding that 9 worker observation. Okay, because we want to update this. Copy our blue curve result and make that the new prior. Again, don't paste it in, paste it in. Oops. I don't want this. See, doesn't like that. What I want to do is paste this in with values. There we go. You see, things get tighter and tighter. They start to pinch in. We're going to see this phenomenon in lecture 5. But let's go back. We now know how to do this. Let's insert between the 7 and the 9 a new column. And that piece of data I said was 5. Right at the end of that lambda set of lambda assumptions. Let me just copy this over. Now we have the same Poisson. It's 18 like it was before, or close to it. But the lambda hasn't changed. But this will change. Now this is going from F all the way over here, all the way over here to I. So when I inserted within this product range, it automatically made room for this new column of data. So just copy this down. Now we're getting something really interesting. Still 7.5. Okay, it's closer to 7.5 than anything else. Okay, from 5 to whatever. And we can actually, if we want, focus our attention somewhere between 6 and 8. Let's focus this. Now, what did we do? We took the result and made it into a new prior. It's no longer row 9. This is the updating process that is possible. What happens if we add more data? Then we can update further and further and further. Adding more data means the model will change from time to time. The result might change. And if it might change, we have to issue a new policy statement about how many workers come in this particular case. Okay, if it changes as you have new data. New data changes things. In our particular case, it kept it pretty constant. And now I'm going to focus this on a max of 8. See if I can get this in there. And a min of 6. Will this work? I'm zooming in. And you see now it moves closer to 7 on the zoom in. Okay, 7.5 is no longer even in the running here. 7.5. Okay. So how many workers? 7 and 7. We don't even have this in here. We don't even, with a lambda 7. Let's see, we don't even, our best lambda, it's no longer that. Lambda, our best lambda is consistent with 7. But 7, not 720, not 740, not, and so on. Okay, and this is what happens, and we're moving towards a curve that is actually kind of interesting here. We're only going between 6 and 8 in this. We're zooming in, if you will. When we zoom in, we get a different result. So how do we square that with reality? Well, that I think that needs an in-person discussion, don't you? Okay, so and look at that versus 10 and 5, which squares up at 7.5, not 7. Okay, so even your assumption about the hypotheses will matter when you perform these numerical experiments. You got to be careful. Right? What if we used 12 and 2? No, I don't get anything because I keep writing in the wrong things there. Okay. Let's get rid of these. Can't even recognize that. Just 12 and 2. Okay. See, it moved down to 7. I think the right answer is probably closer on 7 here. So what is the average of 7, 5, and 9? We have 3 numbers. Oh, it's 7. And this is a famous result. It's called maximum likelihood. We're looking at the maximum a posteriori, given the previous a posteriori as our new prior. Okay, and this is a result that will occur over and over and over again. And it ends up, this is one of the ways we can actually produce something called the normal curve. We can also get the same kind of normal curve from the binomial model, but neither of those deals with normal curve, whatever's on the axis, okay, where the data is continuous. Here we're using integer data. Okay. I'm going to leave you with that. I think that's enough playing around with this model, and I hope you enjoy the picture. Actually, the picture is much more interesting. Okay, as we play around with maxima and minima. Oh, nothing comes up there. There we go. That even moves down further. Yeah, very interesting. How things change when you change the when you start changing the assumptions, one of which is how you built the numerical routine. I'll leave you with that, and thank you very much for your very kind attention.